Good evening, everybody. Miss Kumpf here. I'm calling this video Inclined Planes. Why so hard? And I'm calling it that because I remember in high school finding inclined plane problems so difficult. And then really everything broke open for me when I just had one trick that I learned that made everything a lot easier. So tonight I want to tell you about why are they so hard, and also what is the trick that makes them a lot easier, and how do we solve problems involving this. So the first thing is, why is it so hard? Well, let's draw a quick free body diagram for this object on an inclined plane. First, I've got gravity, just like always. Second, I have for sure a normal force, but which way does the normal force go? Remember that the normal force is always going to be perpendicular to the surface. So if my surface looks like this, I need to find a 90-degree angle to that, and it goes kind of in this direction right here. So again, I can call it Fn or just n for normal. And so already my free body diagram looks a little funny, and I have to imagine that there's probably a little bit of friction here. If I'm starting this object at rest and maybe it's going to slide down the ramp, then for sure friction is kind of in this direction. And remember, friction is always parallel to the surface of the ramp. So why is this so difficult? Well, for sure, here's my xy plane, and what's so difficult is I have gravity down like always, but I have the friction force, which is at some angle. I might call it theta 1, and I have the normal force, which is also at some angle, and it is not in the xy plane either, so I need to break it into components, and then I have kind of theta 2. And so one thing that makes this really tricky is that I have two angular forces. Now that shouldn't be tricky to you because you're so good at working with components of forces, but what are these angles? Are they the same angle? Well, I don't think so. I know that the relationship between them is 90 degrees, but how are these angles related to the angle of the ramp? It makes it really, really difficult. And then problems can get even harder because what if I imagine I'm pushing this block up the ramp and then I have some sort of applied force up the ramp. Friction force is now down the ramp, my normal is still this way, and now I've got all of a sudden three different forces that I have to break into components. I've got this one, I've got this one, and I've got the normal force, and so now I've got different angles in all three forces, and I'm totally lost. So here's the thing that really changed my life in terms of inclined plane problems, and it is actually quite simple. So the trick is this. Notice that something is kind of unique about these three forces right here. The normal force, the applied force, and the frictional force all seem to be either parallel or perpendicular to the surface of the plane. Well, maybe there's something there. Maybe there's some way we can use that symmetry to our advantage. And the trick that really helped me was imagining this whole situation kind of from this way of thinking. If I rotate my problem, so now I've got almost a flat surface. I can think about the surface as being flat where my normal force is perpendicular, friction and applied forces go sideways, and now it's just my gravitational force that goes in this weird angle. Do you see now that I've completely redefined x and y such that these three forces are all in either my x or y direction, and only the gravitational force is now at an angle. So what that means is that my problem got a lot simpler because instead of having three forces that all need to be broken down into their components using sine and cosine, now I can basically create a new frame of reference parallel and perpendicular to the plane, and some people don't even call this x and y, they call it parallel and perpendicular. I've created a new frame of reference where only the gravitational force is at an angle. So let's break out.
So here I can break out the y component, or the perpendicular component of the gravitational force, and the x component, or the parallel component of the gravitational force. And I'm just going to label them FGY and FGX. And oops, I labeled them backwards. I'll fix it later.
And what's nice about this frame of reference is it's not just making it easier to draw our free body diagram, it actually also allows us to see the direction of the motion, because really the object here, if it's being pushed up this hill, is going to move in a direction, it's going to have a velocity that is itself perpendicular to the plane. So I've created a situation where all of my motion is now in one dimension, even though I have forces in two dimensions, and those forces that are in two dimensions are much simpler to model because I have only one force that is at an angle. So I can either look at my situation like this, completely redraw any inclined plane problem as a flat surface where just the gravitational force is an angle, or I can still draw all of my problems in this direction, so I can look at them as they really are, but simply draw my coordinate axes to be parallel and perpendicular to the surface. So whichever of these is easier for you, this is a great trick. Here's the only situation we have, or the only issue we have with this, and I'm going to redraw mine like this because I think it's easier to look at. The only question I have now is, what is the angle here, theta, maybe I'll call it theta 2 to differentiate it from theta 1, the angle of our ramp. What is this angle here? Because I need to know the angle that the x and y coordinates of the gravitational force are at to be able to understand how much of the gravitational is in the x versus the y direction. And for sure, that is going to be dependent on the angle of the ramp. But what is this angle itself? I don't know. So I'm going to do a quick geometric proof once to show you how we can understand how that angle relates to the angle of the ramp. And then once you've seen it, you never really have to do it again. You can just use the relationship that we come up with. So again, my question is, if I completely turn my problem this way, how can I break out the gravitational force into components? What angle is the gravitational force at? So let me redraw my problem this way. And I'm going to get rid of some of the less interesting things so that I can make this problem a little bit simpler. So here's my incline. This is our angle of the ramp. We called it theta 1. I know this incline is kind of like a 90-degree angle here, and so I've got this triangle right here. Once I have my object on here, I know that the gravitational force is directly downward. I've drawn this really long because I want to show you some geometry involving the large triangle I have here and this new smaller triangle I've created here. Well, I know that since the gravitational force is directly down and then the side of my incline is directly down, I know that I've created a 90-degree angle here. Well, don't forget from geometry class that any triangle has 3 angles that must add up to, do you remember? 180 degrees. So in this outer triangle here, just like in this inner triangle here, I have some angle that my ramp is at, I have a 90-degree angle, and I have this angle, which must be complementary to my first angle. So let's play with some numbers here. Let's pretend that my angle of my ramp is maybe 30 degrees. All right, so if I've got a 30-degree angle here, what does this other angle have to be? Well, 180 minus 90 is 90. 90 minus 30 is 60. So this has to be a 60-degree angle. Okay, so if that's a 60-degree angle, what happens when I break out my components? Why does that help me? Well, remember that the gravitational force has 2 components, the y component and the x component is what we're calling them. And so the real question we were trying to answer is, what's with this angle right here, theta 2, the orange angle? Well, now I know that the angle just next to theta 2 is 60 degrees, and I've drawn this angle, right, or this component, perpendicular to the surface. Well, if here's the surface and it's parallel, this is parallel to the surface, and this is perpendicular to the surface, I know that this angle here must be another 90-degree angle. And one more thing you need to remember from geometry class is that the entire line has a total angle of 180 degrees. So if this is 180 degrees in total, this side is also 180 degrees, and so I've got 60 here, I've got 90 here. What must theta 2 have to be? So theta 2 has to equal the whole entire 180 degrees minus the 90 degrees that I already have. So here's the 180 degrees minus this 90 and minus this 60 degrees. And so theta 2 equals 30 degrees again. Exactly the same as the angle of the ramp we started at. So geometrically, we can prove that when we break down, I'm going to turn it again, when I break down the y component and the x component, oops, I have them flipped here. That's silly. The y component and the x component of our forces, if we break down the y component and then the x into the plane, then the angle of the ramp is exactly equal to the angle between the x and y components, or the parallel and perpendicular components of the force of gravity. So what's clever about this is now we can use that to solve a problem. So let's see how it breaks down into our x and y component vectors. Remember that all of these problems start with our Newton's second law, sigma f equals ma. And we can break each of these down into components, so we can say all of the x component forces cause an x component acceleration, and all of the y component forces cause y component acceleration. But because we've changed how we defined our x and y axes, we know that the motion is going to be completely parallel to the plane, and so the motion in the y direction has to be 0. We're not going to move off of the surface, we're only going to slide along the surface. So if the acceleration in the y direction is 0, then the sum of the forces in the y direction has to also be 0, which means that they have to be completely balanced. Well, what y component forces do we have? Just the normal, and I've called that in the up direction, and the y component of the gravitational force. So force normal has to equal force of gravity in the y direction, and that's it. You'll notice this is also why our normal force decreases. When we have a flat surface, an object's entire force of gravity is balanced by the normal force, which is why it doesn't move up and down. But now it's only balanced not by the entire force of gravity, but only the y component of the force of gravity. So if I were to put a scale on this incline, for example, the normal force that the scale would read would just be equal to the y component of the gravitational force. So let's say this is a 30-degree angle still. I know the y component of the gravitational force is the force of gravity times, let's see, this side is adjacent to the orange theta angle. So I know adjacent means I have the cosine. The cosine of the angle times the force of gravity must be equal to the y component, which is why we have only part of the force of gravity. So our normal force is equal to Fg cosine theta. Well, what about in the x direction? Well, in the x direction, I'm probably going to have some sort of acceleration since I've drawn an applied force and a frictional force that are not balanced. So I'm going to keep my mass times acceleration in the x, and I'm going to look into summing the forces in the x direction. So what forces do I have? I have an applied force that goes up the ramp, so that's positive. I have a frictional force that goes down the ramp, so that's negative. But I also have the x component of the force of gravity. Which way does that go? Well, the y component of gravity went down this way, the x component of gravity goes this way, so that I can get this actual gravity, which actually goes towards the center of the Earth. And so in the plane that I've drawn, in the way I've defined my x and y plane, if I'm going to the left, that must be a negative force. So I'm going to call the force of gravity in the x direction negative. And so one last thing, I need to break this down into its sine or cosine. Which trig function do I use? So if this is my angle here, The x component is the opposite side, and so we know that we always use sign with opposite. So here I have negative force of gravity times the sine of the angle. And now I don't really need to use theta 1 or theta 2 because I know that theta 1 and theta 2 are equal. Just remind you of that. So the angle of the ramp is equal to the angle between the force of gravity and the y component, between the entire force of gravity and the y component of the force of gravity. So Fg sine theta minus F force of friction plus the applied force is equal to MAX.